started. Will Troiani will tell us about monads and categories.
Thanks, Dan. Okay, so the motivating question for today's talk is, what is a program? Now, as Dan spoke about in last week's lecture, there is this system which can be constructed called the lambda calculi. Also, as Dan discussed, this is to say Cartesian closed categories. And this is thanks to Lambeck and Scott, and this gives us perhaps a first potential answer to this question. Easy. A program is simply any term in a lambda calculi. In fact, there are many reasons why one might want to extend a given lambda calculi. I should specify as well that this is the simply typed lambda calculus. In order to get this bijection. So down here we have the simply typed lambda calculus. And also, as Dan discussed last week, we can make it more expressive because this only has the power to express quite a limited amount of computable functions. One way of doing this is by adding to your corresponding Cartesian closed category what's called a natural numbers object. And that gives you a bit more mileage. Or you could even add a higher order structure and end up somewhere such as the system F. So these are all notions concerning expressibility. However, this is not the only reason why one might want to extend the lambda calculi. Somewhat orthogonal to expressibility is ease of use or ease of reason about the programs that we're discussing. And so a question that someone could ask is, what structure can we add in order to make the programs easier to use or easier to argue with? It was Moggi's suggestion that we put monads here. So what that means for this diagram is if we have a Cartesian closed category, we can equip it with a monad and this gives us a little bit of extra structure. So this is not adding expressibility, but this is adding just ease of human reason or human use. And this perhaps gets us closer to working out what exactly a program is. So today's talk is explaining what monads are and how it is that they achieve what I've just claimed that they do. So the first obvious question is, what is a monad? Well, a monad is a collection of a functor along with two natural transformations that satisfy some commuting diagrams. So of course, first of all, I'm going to have to explain what all of that means. So that brings us to our first definition, which is that of a category. A category C consists of a class of objects, which I'll denote with capital Roman letters, as well as for each pair of objects, I'm going to ask for a set of morphisms. This will be referred to as the Hom set. The notation that I'll be using is fancy C followed by xy. So this is the Hom set of xy in the category C. And these morphisms are going to have domain X and codomain Y. Okay, I'm not finished with the definition. I also need, for every triple of objects, I'm asking for a function which is going to be our composition function. Which takes one morphism f, that's an f from x to y and g from y to z, and I'm going to ask for g after f from x to z.
Can I just ask, given the way you've written that set of morphisms, we're not restricting the cardinality though?
Absolutely not. But so to every pair, I'm asking for it to be a set. But if I take all the morphisms, that's going to be some class.
Well, but I was asking about a single pair. That one set.
No, I am asking for a set.
Yeah. That wasn't my question. Given it's a set, it has a cardinality. You're restricting.
Oh, I see what you're asking. No, sorry. I'm just. This is more or less for notation. Not meant to confuse anyone about cardinality. Would you like me to change it?
No, just making sure.
Yep. Yep, no worries. Okay, cool. And this is composition. Still not finished with my definition. I also need for every object an identity morphism. Good. And I need all of this to satisfy the following axioms, I'm going to go ahead and write this. So I'm just going to say I want associativity for my composition function, and I just need this to hold whenever composition does make sense. And I also need identities to act like identities. And again, this is just when composition makes sense. So f here is from y to x. Okay, now I'm finished with my definition of a category.
But there are some differences between the definition of category and the definition that I know. Well, yeah, that one I don't mind, that the part that between two objects you have a set of morphisms, but the one whenever composition makes sense, can you give some?
So I'm being lazy here. What I mean to say is, okay, I can write this out better. Just let me free up some space. So when I have three morphisms, there's choice, right? So I'm going to say if let's do this. If H is from X to Y and G is from Y to Z, and then to make it confusing, F is from Z to W, then I've got choices here. I can either compose these first and then get a new morphism, which is going to be from Y to W, and I could then compose that with this function, or this morphism rather. Or I could have done it the other way around. I could have composed these two first, I'll get a morphism from X to Z, and then I compose that with this one to get a morphism from X to W. So I could write that down, but to save time, I just kind of wrote it like that.
Another way to say it is sometimes it's axiomatized with a class of objects and a class of morphisms, together with two functions on the class of morphisms, a domain and a target.
Mm.
And then you can take a fiber product over those maps to, in a sense, formalize the notion of whenever it makes sense. But like there's some quantification. So for all x, y, and z, x, y, z, w, and for all f, g, h, with the corresponding membership, some equation holds.
Okay. More than happy to talk about this afterwards, but hopefully, at least approximately, this makes sense. Okay, so perhaps more important than the actual categories are the mappings between categories. So let's talk about that. So, given two categories, C and D, a functor F from C to D consists of for every object C in C in assignment to an object which I'll denote FC in D. Cool, but categories have more than objects, they have morphisms. And and for every morphism F in C from X to Y, an assignment to a morphism F, which is in D with codomain Fx, with domain Fx and then codomain Fy. Okay, cool. So this can be expressed in terms of an actual function because when we're talking about these Hom sets, we actually are at sets now. So I could have described this in terms of functions, but this is fine. I'm not done with the definition yet. So if we think about what structure does a category have, it has more than just objects and morphisms. It also has composition and identity morphisms, and I want the functor to respect them. So for all x in C, f of the identity is equal to the identity of f of x. And again, I'm simply going to say for f x to y and g from y to z, f g after f, I want to be equal to f of g after f of f. Great, so if I take two morphisms and then I compose them and then map that with my functor, I get the same thing as if I had mapped those two morphisms with my functor first and then taken the composition. That's what this is asking for. Okay, great, that's all definitions. Let's quickly have a look at some examples. I'll hopefully clear the air a bit. Okay, first I'll give you a couple of examples of categories and then I'll talk about functors. So the prototypical example of a functor is the prototypical example of categories is the category set. Which has as objects just any set. So what I'm trying to say is take a set, any set, that is an object in my category. And then the morphisms f from x to y are just functions in set theoretic sense with domain x and codomain y. Okay, great. So let's recall what we need for a category. We need to make sure that we have a composition function, and composition in the category is going to be exactly composition of functions. That is indeed associative. And also we need identity morphisms for every single object. So all I ask for is on every single set, just give me the identity function that just maps that set back to itself identically. Cool, so this is indeed a category. Perhaps after this example, it's not too surprising that other examples of categories are things such as the category of topological spaces, when rather than just looking at sets, I'm looking at topological spaces, and then rather than looking at set functions, I'm looking at continuous functions between them. But I wanted to make the point that not only do categories have to be like set-like and function-like, indeed this is abstract, it can look quite different to that. So as another example, fix a monoid M. Let's just recall quickly that what a monoid is it's just a group where we relax the condition that we have inverse elements. So a set binary operation, we've got associativity and an identity element. Then define, so the category fancy M, the objects are going to be just one formal symbol, star. It can be whatever you want. So the singleton set is what the object is. And then morphisms if M is any element in my monoid, then M thought of as a morphism from star to star is going to be in this Hom set. Okay, great. And then composition is actually going to be multiplication. So what I mean by that is if you give me two elements in my monoid, then I've now got an M1 and an M2, and so I've got two morphisms from star to star. I can compose them to get a new morphism from star to star by just taking M1 multiplied by M2. The only last thing that we need to concern ourselves with are the identity morphisms, but it is, after all, a monoid, so we have an identity element, so that's going to be our identity morphism. So this is, in fact, an example of a category. And also, you might just note that the requirement for associativity of the composition in a category is expressing exactly the associativity of the multiplication in the monoid M. Cool. Okay, let's talk about functors quickly. So rather than giving an explicit, I will give an explicit example, but I wanted to make the observation that functors aren't this mysterious thing that we haven't seen before. They're kind of everywhere. And so as a concrete example, if we're working in algebraic topology, say, then one thing that we're concerned with is separating our spaces. Now, we know that if we have any two pointed topological spaces, so what I mean by that is give me a topological space X and a point in it, and then give me another topological space Y with a point in it, then I can associate to both of these a group. I can associate the fundamental group. So if we think about what's going on here, I'm saying that if you give me any element of the category pointed topological spaces, then I'm able to give you an element of the category group, which is exactly what the functor is meant to do. But more than this, if I have any continuous function f from x to y that preserves the base point, that is to say, if I have a morphism in the category of pointed topological spaces, then this actually induces a map down here, which is going to be a homomorphism between these two groups, which is exactly what a morphism is in the category of groups. And so the fundamental group, this pi1 map, is indeed a functor. Top star, pointed topological spaces.
Just a quick question as well. Your morphisms in the category of pointed topological spaces, do you require that they're both continuous and preserve the distinguished element?
Simply a continuous function from x to y such that f of x naught is equal to y naught.
just is another group defined on non-path connected spaces?
Sure it is. If I take any topological space, I can then look at paths on it and homotopy equivalence classes of that path.
I think maybe what you're getting at is, without choosing a base point, then it would depend on the component. But since we're fixing the base point, it doesn't matter if it's connected.
Oh, yeah. Okay, cool. So, whilst we're having so much fun mapping recently defined objects to recently defined objects, maybe we can get excited and say, can we map functors to functors? Indeed we can. But let's have a think about what that should be. Okay. Given two functors, f and g, which are going from one category C into another category D, so both of them are from C to D, what would a map from F to G be? Well, let's think about what the data is of both of these functors. Well, the functor F is a C-indexed collection of morphisms in D. Similarly, the functor G is a collection of C-indexed objects in D. And so if I want to have some kind of map from F to G, call it eta, then it had better be a C-indexed collection of morphisms in D that are going from F of C to G of C. Okay, so that looks good, but functors carry more than this. They also carry information about the morphisms on the categories. So we need to make sure that this satisfies given any f from, let's go from C to C dash, and this is in, given any morphism C to C dash in C, let's think about what we have. I have a morphism from f of C to f of C dash, that's given by f of f. I also have a morphism from G of C into G of C dash, that's given by G of f. But I have more than this. I also have these morphisms up here. So I know how to get from f of C to G of C, that's via eta of C. I know how to get from f of C dash to G of C dash, that's via eta of C dash. And so whenever I have this set up, I ask for this diagram to commute. Given any f, the diagram commutes. Cool. So whenever for f, g from C to D, we have such a collection eta, we say eta is a natural transformation from F to G. Categories, functors, natural transformations. Good. Okay, let's have a look at an example of this. So again, I'm going to fix a monoid. M along with some multiplication. Okay, so what do I need to give you in order to give you an actual transformation? I better give you two functors between two categories. So let me define first the functor T, which is going to go from the category set into the category set, and it doesn't do much. All it does is it takes the set and it just takes the cross product of x along with m. Okay, that's what it does on objects, but what does it do on functions? Where given f from x to y, I will ask that t of f, so t of f is going to be mapping from x cross m into y cross m. So if I give it any x cross m, I'm going to get back a y cross m, which is just going to be f of x to m. Cool, nice and simple functor. And I'm going to define an actual transformation from the identity functor to this functor. So then for any set x, take, okay, I said that I was going to give you an actual transformation from the identity functor into t, but I'm actually not going to do that. I'm going to give you an actual transformation from the square of t into t. Now, what the square of t is if you notice that this functor t is mapping from set to set. So I claim without proof that if I have such a situation, I can just compose that functor and I get back a functor. And so I'm able to define an actual transformation from the functor t squared into t. I'm going to do it like this. Take mu of x, which goes from t squared of x into t of x, by, well, what is t squared of x? It is x cross m. And then what am I going to do? I'm going to give you back an x cross m. Well, I have a monoid, so I have a multiplication. So let's just make this m1 dot m2.
So have you just defined the unit of the...
This is going to be the multiplication. The unit simply sends x into x comma the unit element of the multiplication. I'll explain Sam's question and mention what I just said in just a few minutes. Okay, so this is an actual transformation. Okay, the proof of this, well, what do we need? We need given f, which goes from x into y. If you remember what the commuting diagram is, oh, well, it's right there. I don't need to draw out the diagram again. But given f from x to y, okay, so if I go around this side of the square, I need to get the same thing as if I go this way around the square. So what am I asking for? I'm asking for, let's go top then down. So I'm looking at mu of y composed with t squared of f. And then if you give me an x and an m1 and an m2, okay, I need blah, blah, blah argument is equal to going around the other way. So let's see if we can get that. Okay, this is mu of y of t squared of f applied to this. I move it in one bracket and lose a t. So I get x m1, m2, and then playing the same game, I get f of x m1, yes, m2, and then mu y multiplies the two monoid elements. So this is simply f of x m1 times m2. Okay, cool, but then the idea, and this is kind of what's going on with these natural transformations, is I could have gone the other way, right? I kind of applied f and then I multiplied, but I could have multiplied and then applied f. And so reversing that, what that is to say is I could have done t of f of x m1 dot m2, and that's going to be equal to t f composed with mu x of x m1 of m2, which is exactly what I need for naturality. Maybe you guys can't see, but you need the naturality diagram. Okay. Any questions? Looks all right. So this is a bit of a suggestive example, as suggested by Sam. So this actually leads on to the definition of what a monad is. Let me give you the definition of a monad, and then I can point to a few things.
Can I ask you a question?
Of course.
If this was just a magma, not a monoid, would this argument still work?
If this was a what, sorry?
Just a magma, so a set of
Oh.
binary operation.
Well, if
What
we...
we've done so far still work?
Oh, yes. Good question. But it won't be a monad. So the next thing I'm going to write down is that monad is going to require associativity of the multiplication and that the unit acts like a unit. But as an actual map, yeah, this would be fine if we drop associativity in unit, which is a magma. Is that correct? Okay,
Yeah.
cool. Okay. So definition 4. What do I want to say? So a monad T eta mu on a category C is a triple a monad on the category C is a triple. Where T from C to C is a functor, eta, and we're going from the identity functor on, so I said functor, the eta natural transformation is going from the identity functor into T, and mu, which is going from T squared into T, are natural transformations. Okay, so it's those three things. I need to satisfy commutativity of a bunch of diagrams. So let me draw those up. Okay, for all objects in our category, well, let's think about what happens if we go from T cubed of x well, the idea is that if this is mu of x, so if I'm multiplying, well, I kind of have a choice here now, right? I could have taken the multiplication map that's associated with x and then applied the functor to it. Or I could have just taken the multiplication associated to the element of the category Tx. Okay, and I'll ask for that to commute. And then also, no squared into T squared of x. Again, I have a similar kind of thing. If this is my multiplication, then there's two different ways that I can get from tx to t squared x using eta. I could have applied my functor to, that's a mu when it needs to be an eta, to eta of x. And then this is the identity morphism. I could ask for that to commute. Or I could have gone the other way. And the other way is, I could apply, well, I could look at the eta associated to the object of my category T of x. Okay, so what am I actually saying? The diagrams that and that commute. Cool. Now, these extra conditions are going to give us a monad, and then if we look at our example, that's going to get us all the way to a monoid. Yes?
On the second diagram that you just drew,
Yeah.
the left-hand triangle,
Yeah.
on the top arrow, that's figure of A to X.
Yeah. So A to x goes from x to tx, apply the functor t to that.
So it's basically three different equations, right? One for each of those sort of shapes you've drawn.
Yeah. So this is nothing but saving space. We've got three commuting diagrams here. Okay, so an example with t from set to set as defined earlier along with mu also as already defined, and the following, which is just going to be our natural transformation eta for any object x in C, eta of x is going to go from x to t of x, and what it's going to do is it's going to map an object to x. So remember what this is. This is the Cartesian product of x on with the monoid. So let's just take that to the identity element of the monoid. Yeah. So claim this defines a natural transformation such that T eta mu is a monad. Okay, and I won't prove that, it's simple. All right, so the next kind of phase of my talk is to then explain what any of this has to do with programs and computing. So before I get into that, does anyone have any questions about anything I've said so far? Yeah?
So you know how there's three equations that usually define a monoid: there's associativity, left identity, and right. Would it be fair to say that each of those equations gives you one of these three diagrams you've drawn?
I don't know what you mean by left multiplication and right. If I have...
associativity, left identity, right. So
Yeah, sure.
EX equals
Yeah.
X.
Well, we're going to... So the way that we're presenting the... So if we were to define T mu eta in such a way to try and prove that M is a monoid, is what you're asking, what lines up with what? Is that what your question is? Okay, cool. Well, this, it's just placement of where I put the E, isn't it? Yeah.
The T eta x will put it sort of to the left, and the eta will instead put it on.
We'll put it on the right, exactly.
So it's,
Yeah.
as you said, sort of left and right.
Okay. Cool. I was going to pause for thought. I feel like there was something that I wanted to... Oh, no, that's fine. Okay, cool. Let's move on to programs. Okay, cool. So, how does this help us reason about programs? Now, let me give you kind of an example. Say I was looking at a program, I have it on my computer or on my Turing tape or whatever, and I'm saying to myself, how can I model this? Then one easy first thing to say is, okay, why don't I just look at the input-output pairs? So we're just looking at a mathematical function. Easy, a program is just a mathematical function. Well, there's a few issues with that. One example is, what if a program never halts? Or what if it fails to return some output or something like that? Then a mathematical function requires to give an output for every given input, so that won't work. Now, one perhaps obvious solution to that problem is to say, can't I just kind of give my domain, my codomain, some special symbol where every time the program fails, on that input, I just map the function into that special symbol, and that's just going to represent failure. Yeah, that is a good idea, and in fact, that's exactly what monads do. So I want to argue for the rest of this talk that that is the kind of thing that monads are doing, and the way that I'm going to convince you of that is in two stages. First, I'm going to define a new thing called Kleisli triples, and I'm going to convince you that they do that, and then I'm going to convince you that Kleisli triples are monads. Okay, so that leads us to definition 5. Let me make sure I get this right.
Maybe it's worth noting that we're following Moggi's presentation and doing this.
This is following Moggi's presentation. So Moggi's 91 paper, Notions of Computation, that's what we're following here. Okay, Kleisli triples, what are they? A Kleisli triple over a category C is a triple, no doubt, T, eta, and then this star operator, where T is a function from the objects of C onto the objects of C. I'm going to make this really explicit and say from the objects of C onto the objects of C. I'm not asking for anything on the morphisms, so this is not a functor. So just be careful of that.
So that's just a non-direct function.
Well, it's not a set, maybe.
Oh.
But yeah, generalized function. It's a generalized function. Okay, and then eta is a collection of morphisms from C into TC and that's the end of the story. So this is not an actual transformation. I haven't asked for anything in way of commuting diagrams. Okay, and then the star operator for every morphism of the form C maps into T of C dash, I want a new morphism which I'll call f star, which is going to go from t of c into t of c dash. Okay, I'll say a word about this in a second, but I want to finish with definition first. We have some axioms. So for any hope of this being a monad, we better. And they are, for all C in C, we want eta C star to just equal the identity on T C. Maybe you guys are seeing that chirality come through already. F star composed with A to the C to just equal F. And okay, F star composed with G star to equal F composed with G star star. Again, like whenever the composition makes sense. Or whenever composition is well defined is maybe a better way of putting it. Okay, cool, that's a Kleisner triple. Maybe it looks a bit strange at the moment. So let's look at an example. Okay, let me formalize that kind of intuition that I gave a few minutes ago about a function that might fail on a given input. Okay, so Kleisner triples are over categories, so I'm going to take the category set, and what I'm going to ask for is this following function. If you which goes from set to set, which is if you give me x, just map that to x disjoint union some formal symbol which I'm going to refer to as failure. Okay, cool. And then eta of x goes from x into tx, which is x, right? Which is just going to be inclusion. X, that's fine. Okay, great. And then the star operator. Now here's the point. So, given f from x into ty. Now here's the idea. Say we had down here g, which was going from y into tz, right? And then say I wanted to compose these functions, because we've got these two functions, and I've said, okay, cool, they might fail, so let's do this thing to our codomain. But I still want to be able to talk about composing these functions together. So how would I do that? I could write g after f, but it's ill-defined if I do, because g doesn't know how to take things that might have the opportunity to fail. But that's exactly what star is doing for us. It's telling us it's telling a function that doesn't know how to eat things of the form t of a to be able to do that. So if I go ahead and make this a star, then this composition now will be defined. And with this intuition in our minds, let's think about this. Given f from x to ty, well, let's define f star of x to be the following hybrid function. It's pretty obvious what I'm going to do. If x...
Sorry, maybe we should start.
Oh, sorry, did I? I need to tell G how to eat things of the stuff. Silly me. Okay, so this is just going to be f of x if x was already in by x. And then I'm just going to pass the failure through if x was failure. Does that make sense? So why does this help us reason with programs? Well, the idea is that I can take these simple looking functions and then look at, well, Moggi uses this phrase notions of computation, which I quite like. Let's call the idea of a function potentially failing a notion of computation. What we can do is now look at simple functions and then define the Kleisli triple to observe that notion of computation, and then we can just talk about it in these terms. So we still have composition, and we're able to look at this more abstract idea. Great. There are other examples of Kleisli triples that you can take, things that are able to deal with potentially having a dependency on the state of the machine or something like that. I was going to give that example, but we're really pressing time at the moment. So let me get to the punchline and tell you how this is exactly the same thing as what a monad is. So here's the theorem. So let me get the same right. Kleisli triples on a category C. Okay, proof. So I won't fill out all the narky details of making sure that the axioms are satisfied and that naturality is satisfied, but I'll tell you where the pieces go. So given a Kleisli triple T eta star, okay, I need to extend T in order to be defined on morphisms. Given f from A to B, well, what am I going to say? T of f has to go from T of A to T of B. Well, I have eta, which knows how to take things from B to T of B. So let's do eta of B after f. And so now at the moment I'm going from A to T of B, but then star knows how to send that to something from T of A to T of B. So let's take the star of that. Cool. Eta just is eta. The axioms are able to tell you that this is telling you that we have naturality of eta, so I don't need to do anything there. And then lastly, I need to define mu for you. Well, we can play a similar kind of game. I need to go from t squared of x to t of x, and the way I'm going to do that, well, I know the identity on t of x just goes from t of x to t of x, and then star knows how to send that to t squared of x to t of x. So let's just make that the identity of t of x, and then star it. Cool. Then t eta mu is a monad. And then for the reverse direction, So how do I get t from t? This is the easy direction. Just forget what it does on the morphisms. Eta is also fine. And now we just need to work out how to get a star operator. Given f from A into TB. Well, let's think about what I can do. I could apply t to this, and I'm going to end up, so just remember what we're trying to do. From f from A to TB, I need to get an f star that goes from TA to TB. Okay, so given f from A to TB, I could apply t to this. I'm going to go from TA to t squared of b, but that's fine because mu knows exactly how to get from t squared b into TB. So, take f star. Now, what did I just say? T to f, and then mu of b. Done. Then T eta star is a Kleisli triple. Cool. Are you guys willing to stick around for 5 more minutes while I make one more point? Yeah. All right. This will be the last one, I swear. Okay. So, to conclude, I want to mention that monads aren't actually the most fundamental notion of what's going on in this picture. Indeed, every pair of adjoint functors gives rise to a monad, and every monad gives rise to a pair of adjoint functors. The fact that every monad gives rise to a pair of adjoint functors is proven by this construct called the Kleisli category. So if you give me a monad, I can form a Kleisli category, and then from that, I'm able to build a pair of functors between those two categories, and we can show that they're adjoint. So that's lurking kind of behind the scenes here, and adjoint functors will be really important going on in this seminar. So I just thought I'd quickly mention that they kind of are here as well. And lastly, monads don't solve all the world's problems. And as a concrete example of this, earlier I mentioned that failure is kind of an obvious example, but let's take another example. Let's take something that depends on state. So if we have a function, and now I want to give that function the power to have a dependency on state. Okay, cool. Say I have a monad that's able to do that. So now I've got two monads. So let's call T failure, and let's call S state. Now that's great, but out in the real world, you might have both. You might have some program that both might fail and also has a dependency on state, or something way more complicated than that. Well, that's fine. You might just say, great, let's compose these categories, let's compose these monads, and then we'll get one that has both. But that doesn't work, and that's what I wanted to mention. So I could take the composition T of S, but is this really a monad? The answer is no. Sorry to give away the punchline. But the reason why is because what would mu of Ts be on some given object? Well, I need to go from Ts squared of x into Ts of x. Okay, great. Well, Ts squared, that's Ts of x. Now, let's keep in mind that these are both monads themselves, so I have a multiplication associated with T, and I have a multiplication associated with S. So if I was able to get this, the problem is this S and T. If I could swap them, then I'd be home and hosed. I could then make that TTSS of X, and then I'm one multiplication of S and one multiplication of T away from having a monad. So what I really need is some kind of natural map that knows how to swap the monads. And this is the problem. This need not exist in general. Sometimes it does, and when we do, we call this a commutator for obvious reasons. But this is really the problem. You might grab your two notions of computation that you want to work with and then you want to combine them. Well, there's really no obvious way of combining them. That's kind of the problem. Cool. Thank you for listening. That's the end of my talk.
Questions for? Question. Do programmers actually use this?
The theory or monads? They use...
Yes, let's say monads.
Yeah. Well, this does come up in the real world of computer programming. For example, in the computer language Haskell, monads are used extensively. So when people were first trying to build functional programming languages, they were trying to do it in lambda calculus, and then they extended it out to system F, etc. And that was when they started realizing that they needed something to make this a bit easier because it was getting complicated. And that was when people first started thinking about monads. And yeah, that's exactly what Haskell uses. So yeah, we've got this in the real world as well.
What's that, the maybe monad?
The maybe monad is the failure one. That's exactly what it is. And there are others. I don't know. We'll talk about that later once I've checked my notes. I think state is, yeah, IO, I think, yeah. Checks.
You don't insist in the definition of a cloud triple that it's a functor or a natural transformation, but it seems like you may as well.
It seems like I do.
Because you don't
So-
there's not a whole way to turn it into a functor and a natural transformation.
Because it's scrambled is the idea. The one's not scrambled. This is naturality of eta.
Yeah.
But if you want to get mu, and you have to use t squared of f, right? Then t squared of f is defined of mu as well, which makes sense, doesn't it? So if I have f to t of f, a t of f, I used mu in that definition. Yeah, so it's all scrambled. So it is the information of a monad, of course, I proved that.
Yeah.
But the information is scrambled up in such a way that... So I would love to give you a purely programming perspective motivation for these axioms, right? And I would probably make the argument a bit stronger, but so I'd be able to say these truly arise naturally in programming, and monads truly arise naturally in mathematics, and then I can combine them for you. But I can't do that at the moment. That's
Once you
something
see the
more.
example, it's sort of clear why, at least that example comes from the failure state, right?
Yeah.
And it's not at all clear what other weird objects, what other weird collision triples you can come up with that maybe don't have a natural interpretation like that.
The only ones that I've worked with are the ones that do have those natural interpretations, because that's why they're picked out, because they do have those.
It's not that obvious from the definition, though, that there aren't.
That there aren't weird ones. Yeah. Well, any weird monad will give you an example.
Because in practice, when you actually create a monad in Haskell, you don't have to check the axioms. Nobody forces you.
Yeah.
It's sort of pre-Kleisli triples that are just some data. That's what in fact is in Haskell.
Yeah.
Do you have an example where there's that fails? There's no commutative. There's no.
Yeah, I was thinking about this. I think state and failure fail. I'll give you a super hand wave you want, and you can press me for a more rigorous one if you want it. So S to T, I give it the power to fail, and then I say that depends on state. So what that means is there might be some states in which my program fails. Cool. The other way around is I say now it has a dependency on state and it might fail. So it means no matter what state I give it, it might fail on absolutely all of them. These are two totally different ideas. And there's no way...
Well, wait, can you say that more slowly? That was...
So okay, I need to give you what S is. So if I have S of X, and I want to say that X now depends on state, then the way that I'll... So first it depends on state, and it alters the state. So to alter the state, I just make it return... Okay, maybe this is slightly confusing notation. Let me do that. These are two different S's. I fix some set of states, right? And that's what my S is. And then capital S, I guess, is going to be the state monad. So I argue that this is capturing the notion of state, And the reason why is because now, rather than just having something of type x, it's saying, give me a state first, and then it'll give you not only something of type x, it'll even give you a new state back. Okay, cool. So now if I have f from A to B, I need to look at S of f, which is a bit wacky now. This is A cross S, S to A cross S to S to B cross S. And yeah, there's different ways you can write this. I think the clearest cut.
I don't want to interrupt you, Will, but you said you had some sort of time constraint with 3 minutes.
So I've organised someone else to look after, but thank you. So what is this going to be? This, I'm going to describe a function that returns a tuple. So imagine there's an S here that you could apply to it. Okay, so first what we do is we apply.
Do you want to name the
You
thing
want
you're after?
SF of G, maybe, right? G is a function from S to A cross S. Then we got one.
Yes, that's what I want. So first I apply, yeah.
So you also want a little S.
Yeah, I was thinking I could write this where you see it as like S coming in from the side. So yeah, I could, let me, okay. S of f takes in G and an S, and then what it gives back is a B and an S, and the B that you can give me is first give me the tuple AS that depends on this S, and then project down onto A, and then give that to F. And then I can do the exact same thing, but project onto S instead. And then I don't need F. All right, have I written something that makes any sense? So G of S, and then give me the A, and then map the A, that gives me a B, and then G of S, and then just give me that S. So that's dependent on the S. Okay, cool. So this is the function. Okay, cool. So now this is why I didn't want to write it down. Now the idea is I need to compose this with T on the left and on the right, and then look at the two things that I get and argue that they're different. So let me maybe point from this direction. If I were to apply T after this, right, then now I get disjoint union, failure. Okay, cool. So what's this kind of describing? This is saying I have a function that now either depends on my state, or it will just completely fail all the time, totally irregardless of what state you give me or anything. I've thrown all that out. Okay, cool. Alternatively, if you had done it in the other direction, then the failure is in here. And this is saying something slightly different. It's like, I'm a function that depends on state, and on some of my states I'll be totally fine, and on some of my other states I might fail. These are seriously saying different things, so there's no, you wouldn't even want them to commute. If we have a system that starts telling us that these are the same thing, it's kind of not even a good thing.
Could you find a non-invertible transform between them?
Yeah, in fact, I think there is one. But, so one doesn't actually need ST and TS to be the same. It's just they need to be isomorphic. That would be one way to get a distributed law. I think you may have chosen an unlucky example, so there is at least one natural map from ST to TS, which sort of, ST would have, I've written the opposite of one. So from this one, so that's TS, right?
This is TS.
Yeah, so here's a map to ST. So if I take a function from S to X cross S, just take that function. But if you give me the failure, then I just take the identity function on states. So if the program fails, then anything states. If you write down ST, you'll see.
Oh, I see. Because we don't really need to go back. Yeah, and that's kind of how I argued it, is I can't go back. Okay,
So
that's a good point.
I think you've argued successfully. I think
That ST doesn't go to TS.
right.
Yeah, okay.
But I think I haven't checked the community diagrams.
No, but that sounds right.
So, but in general, there are pairs where this doesn't, there's no reason to expect, or in fact, they cannot exist distributed.
Cool.
Questions for Will?
So I missed your explanation of how monads relate to programming. Can you explain that again?
So monads are the same as Kleisler triples, and then I claim that Kleisler triples relate to programming. This is the hand-wavy kind of notions of computation thing that I mean. Simplify your system. Look at just your inputs and your outputs. Okay, cool. But programs do more than that. What do they do more? Oh, sometimes they fail. Cool, sometimes they fail. I've got a concept in my head. I want to try and like make a monad out of that idea and I'm trying to tie down. That's like the formalization of an intuition that I have. To do that, try and find a way of altering the codomain of your maps, right? That's what T does in a Kleisler triple. It's easy, it's not doing anything on functions, so I just need to alter my objects. And then you're kind of done. Then you might want to compose your functions, so you really need a star operator, right? Are you comfortable with what I mean by that? So if I do f of g, g might not be able to take things of form t of the codomain of the previous function, so I need to be able to lift functions. So star and t are now motivated, and then for eta is usually required to be an injective map, so I guess this is a way of embedding the original functions, the input-output pairs into the program, so they're still kind of there. That's kind of dodgy, but I think that's about the best I can do.
And the way Moggi says it is you're embedding values in computations.
Yeah.
Whatever you want to interpret that to mean. I mean, one way to answer it is simply to say that, well, as defined in my lecture, a programming system was a lambda calculus. By that diagram you drew at the beginning, if you extend a Cartesian closed category by adding a monad, that gives you some new logical system which kind of extends the original lambda calculus. And that is a programming language in some formal sense. And that's, for example, what the underlying core language of Haskell is. That kind of programming system. As for, it's clearly not necessary to say monads. You can have a functional programming language and never say the word monad, but you'll have to fake or find some other, maybe perhaps less conceptual way of embedding things like failure or state into the original lambda calculus. You can do that. Lambda calculus is as expressive as Turing machines, and you don't have types. So it's not a question of whether you could handle state in lambda calculus. You can. But maybe you'll do it in some ad hoc way by like Gödel numbers or something. So you don't want to think in that setting, even though you could express your programs there. And the idea, which is only partly realized for these kinds of reasons, is that monads is a way of saying what you want to say in an idiomatic way within functional programs. Sorry.
No, that was much better than I could have done.